All right, so in this video, we're going to introduce the idea of hybridization. Um, hybridization, or hybrid orbitals, is going to be something that we think a lot about when we think about bonding. Now, you already know some stuff about orbitals. You have some pretty good familiarity with atomic orbitals. Your atomic orbitals are your s and your p orbitals that you can define for an individual atom. Now, those individual atomic orbitals don't make sense, though, for when things bond. When things bond, they start to form molecules, and you get your molecular orbitals. The conversion between an atomic orbital to a molecular orbital will go through a process called hybridization to kind of like describe why things can actually form bonds. This part right here, we're going to give you just a little bit of a taste. You'll learn a lot more about what these orbitals are and actually be able to like define them mathematically through wave functions in physical chemistry, which will be something that if you're a chemistry major, you'll take. If you're not a chemistry major, then that can just live in the ether. So we know stuff about atomic orbitals, an s orbital being like a sphere, a p orbital being like a dumbbell. Here, there are some colors associated with those. Those are your phase, it's not an actual charge. And these are describing where your electrons exist. Now, a node is going to be a location, like for example, in your p orbital, right here at that center spot. This would be depicted as a pz orbital because it's going directly on the z-axis. There's also a px and then a py going on the x and the y-axis. That node is going to be a location where there are zero electron. There's zero probability of finding that electron existing. Now, when you take atomic orbitals and you mix them together to form a bond, you get molecular orbitals. So the two most common that we're going to talk about are going to be sigma, or single bonds, and pi, which are double bonds. And these are going to be when you get your interaction between your orbitals. So s orbitals, both being spheres, if you mix those together to form a bond, so remember, this is like, for example, with one atom, and here's another one, so you have your kind of like two dots where they're located. Those orbitals can come together and form a sigma bond, or a single bond between your different orbitals. You can also do the same thing with pi orbitals. Pi orbitals sitting above and below, where here's like the center of your atom. Those can overlap. Now, it is important that those have the same phase. So right here, this is actually showing one that are out of phase. So these cannot overlap because one of these is clear colored where the other one is shaded. In order to form one, you would need to take and you'd need to rotate one of them around to get matching phases. Otherwise, they'll form what is known as an anti-bonding orbital. Those will be known as sigma star or pi star, where they don't match. Those are very, very high energy states. Your pi bond, though, can form where you get interaction above and below. So one thing that we need to kind of depict, though, is this individual S and P don't do a really good job describing most of your molecules. So we need to get what is known as hybrid orbitals. And there are going to be three main types of hybrid orbitals that we're going to focus on: sp, sp2, and sp3. And these are going to be mixing of your s and your p orbitals together to be able to more accurately depict what that atom that's going to be involved in bonding looks like during that process of bonding. So in general, the number of your hybrid orbitals are just really just going to be a combination of like your s and your p's. So maybe kind of like unsurprisingly, if we wanted to not write this out in math, if you have an s orbital and a p orbital and you mix those together, they make an sp orbital. If you have an s orbital and you have two different p orbitals, they make an sp2. And then if you have an s and three p orbitals, they make an sp3. So it's really just how many orbitals you're mixing will give you your descriptions. Now, why does this matter? Let's go ahead and think about carbon for a minute. Let's go ahead and write out our electron configuration for carbon. We know that carbon is 1s2, 2s2, 2p2. And we can draw and kind of fill out our electrons here. So this would be like our energy levels where we have our 1s, our 2s, and then our 2p. We can go in and we can fill these with electrons. So we have a completely filled 1s, we have a completely filled 2s, and then our 2p has 2 electrons. So I'm going to put 1 in my 2px and then 1 in my 2py. I'm not going to pair those up because I have to follow my rules where I put 1 in everything and then I go back and fill in. Now, if we look at this structure here for our depiction of our electrons, our question is going to be, does this make sense to what we think about with our Lewis structure? For our Lewis structure, when we draw a carbon with 4 single electrons. These single electrons are going to be where we get bonds. Now, if I look at my valence electron, which is my 2s, I have a 2s, which is paired up together, and then I only have 2 orbitals that have a single electron. So right here, this orbital is ready for bonding. This orbital is ready for bonding. This orbital here, which we show in green, has no desire to go bonding because it's nice and stable. And then this orbital here in green doesn't have any electrons to contribute to a sharing of electrons. So this depiction, as we have shown, would suggest that carbon can actually only undergo 2 bonds. But we know that's wrong. We know it wants to go 4 bonds. And that's why this individual atomic view is not that helpful. So what we're going to do is we're going to mix or hybridize our valence electrons, our s and p orbitals together to make brand new orbitals, which can do a much better job at depicting the bonding that's going to exist in our carbon. So we're going to hybridize or mix our 2s and our 2p orbitals together to form our hybrid orbitals. So we're going to take this and we're going to hybridize. And this isn't like a physical process. You don't like add heat or add like some magic powder to happen. It exists already. But we're going to go through and in terms of our energy state here, we're going to still have our 1s, and then our 2s's are all going to be mixed together. So we're going to mix this 2s, our 2p, and our 2p. And overall, that's going to be 4 total orbitals that we're going to mix together. So we're going to get 4 orbitals back out, and these are all going to be our sp3s. So 1, 2, 3, 4, and each of these are going to be an sp3 orbital. And that's going to be a mixture of our 2s and our 2p. And energetically, it's going to sit in between here. It's going to be a little bit higher energy than our 2s and a little bit lower energy than our 2p. Now we can go through and fill these with electrons. So we have a total of 6 electrons that we're going to fill in. So we're going to fill in our lower one for our 2. We have 4 more that need to be added. So there's 1, 2, 3, and 4. And now we look at this. There are 4 orbitals that have exactly 1 electron. That is a perfect depiction of our state for our Lewis structure of carbon. So rather than this depiction of our 2s and 2p's, a much better version to describe the actual bonding that will exist in carbon is saying that these are sp3 orbitals that are going to be involved in bonding. And that's really all hybridization is. It's just simply saying, how can we actually mix orbitals from our atomic state to better describe what actually occurs when we have bonding? Now, this drawing of our energy levels and actually physically mixing is a lot more involved. We don't need to do that almost at all. But I wanted to give you a little bit of that theory in our background. Most of this is actually going to be tied to our VSEPR geometry. So in class, we'll do a kind of quick refresher on VSEPR and then thinking about how that corresponds to actually figuring out our hybridization of our molecules. But our kind of key takeaway here is there are going to be these 3 new types of hybrid orbitals, our sp, our sp2, and our sp3. And these are going to be made by mixing our s and p orbitals to better describe what we see when we have bonding.